Welcome. Today we're going to be covering the Guide to Computer Forensics Investigations. This is the 6th edition. The material all comes from Cengage. They own and control all copyright material. I'm just providing video lectures on the individual chapters for my courses using this textbook. My name is Arthur Salmon, and I'm going to be working with you throughout this book. Thank you. Chapter 8 is about recovering graphic files. So in this chapter, we're going to be describing the types of graphic file formats, explaining types of compression. We're going to be looking at how to locate and recover graphic files through our hex. We're going to be describing how to identify unknown file formats, again, looking at our hex values, and explain copyright issues within graphics. So let's jump right on in. The first area is recovering a graphics file. So first of all, graphic files contain some type of digital photography, art, image, three-dimensional, two-dimensional, text data that's converted to an image, a scanned replica. It's an image. It's a data file that is depicting an image. We have a few different types. We have like a bitmap image. That's a collection of dots. We have a vector graphic that's based on mathematical instructions, and we have a metafile graphic, and that's a combination of both a bitmap and a vector graphic file. There are a few different types of programs that are dealing with graphic files. We have our editors and we have our viewers. Our editors allow us to edit the graphic file. Our viewers allow us to view the file. So let's dig a little bit deeper. A bitmap image is a grid of individual pixels that are combined to make an image file. A raster image, also a collection of pixels. Basically, the difference is the pixels are stored in a row, and the raster image is better for printing. So when we're looking at the actual overall image quality, we have a few different things that we need to look at. One, our print quality, our actual data quality of the individual file, and the screen resolution or the screen file. Because how we look at a data file, we may not want to recognize it, but when we open up a data file on our computer, our screen has to display it. So if we have a bad screen, or if there's an issue with the screen resolution, it might hamper the detail of the photo. And oftentimes, modern day operating systems are smart enough to realize that, so they may limit or they may scale down the image file so that when you do open it, instead of opening it full screen, it will open it as a zoomed in version of it. Image quality also has to do with the software, and that will contribute to the image quality. Again, that's going to be based off of the software drivers, the video drivers, the display drivers, because again, that crisp image is really based off of the display of the device you're working on. Also, dots per inch DPI, as well as contrast, as well as the number of color bits per pixel. All of these have to do with the quality of the image. Typically, the more color, the more DPI, dots per inch, the larger the data file. But all of these go hand in hand with the image quality. Now, when we compare that to something like a vector graphic, the vector graphics are going to use lines instead of dots for displaying images. So they're going to store the calculations for the drawing of the lines and the shapes. They are typically smaller than a bitmap file, and they do preserve the quality when the image is enlarged. Where a bitmap, as you try to scale it up, as you try to enlarge it or blow it up, the DPI don't always scale very well. Examples of vector graphic tools are things like CorelDRAW or Adobe Illustrator. Those are two of the big ones. Adobe Illustrator probably being the larger of the two. So our third type is our metafile graphic, and again, that's going to be a combination of both. The Metagraphic combines both the raster and vector graphics. For example, A scanned photo might be the DPI. If there's text or arrows, that'd be our vector. So the advantage and disadvantage of these are basically when enlarged, the bitmap part loses quality, so that's one of the pros and cons. So what are some of the file formats? We keep saying graphic file, but are there specific types of files? So a standard bitmap are things like a PNG or portable network graphic, a graphical interchange format, a GIF, a joint photography expert group or JPEG, tagged image file format, a TIFF, a Windows bitmap or BMP, where some standard vector files are things like the Hewlett-Packard Graphical Language, HPGL, or AutoCAD DXF. You're going to notice a lot of the file formats that you're used to are going to be a standard bitmap. Only when we're working with CAD or graphical, large graphical files like that will we see a vector. And again, that's not a hard, fast rule. That's just things that I've noticed through experience. We have some non-standard graphical files like a TARG, a raster file, a Photoshop file or an Illustrate file, Photoshop being a .psd, Illustrator being a .ai, scalable vector graphic, SVJ or SVG, Paintbrush, which is a PCX, and there's more. These are just a very short list, but you're going to notice most of what users interact with are those bitmap files. So witnesses or suspects can create their own digital files, digital photos. The interesting part here is how we save the contents. When we're looking at a digital photo from a DSLR camera, the camera might save the data as a JPEG. However, the camera itself actually stores most of it as a RAW file format. And that RAW file is a raw capture of all the light on the sensor. Drastically larger, but all common expensive DSLR cameras, anything over like 50, 60 bucks, have the ability to do a raw file format. Again, these are more like the digital negatives, again, typically found on higher end digital cameras or the DSLR type cameras. The sensors in the digital camera simply record the pixels on the camera's memory card, where the RAW format will maintain the best picture quality, but you're looking at a large size. To examine the RAW format, you need a program capable of opening RAW. Photoshop, Adobe Photoshop is going to be one of those big ones. The biggest disadvantage is it's proprietary. Not all image viewers can view these formats. Again, you need a specific program to open a RAW. Photoshop is going to be your best friend here. The process of converting a raw picture data to another format is called, I can never pronounce this word correctly, demoscalicing. I butchered that one. I've never been able to pronounce it. Basically, when we're converting, it's a demo scaling file, essentially. So when we're examining the exchangeable image format, or the metadata, the specific data on the image, we'd be looking at the exchangeable image file, the XF format. This is commonly used to store digital photos. It was developed as a standard for storing metadata in JPEGs. The XF is essentially viewing the metadata for our graphical files. So what's the point of the XF? When we're looking at any metadata, that's what we're expecting to see. When we get an image file, we want to see the camera, we want to see the GPS coordinates, we want to see the extra data about the photo, and that's what XF does. So examining the contents allows us to view that extra part. Investigators can learn a lot of detail from the digital device that captured it. The focal point, it can look at the image, the camera, the GPS coordinates. It can look at when and where the photo was taken. So there's a lot of detail. Viewing the EXIF JPEG, the metadata does require a specialized program, typically an EXIF reader or a viewer or some form of forensics tool. The EXIF file does store the metadata at the beginning part of the data file. And we're going to look at the data file here coming up. So, I mean, don't stress too much about that. Here is a perfect example of the EXIF picture file and the JPEG picture file. You're going to notice they look almost identical, but the difference is the EXIF picture file houses data behind the photo. So what does that mean? This is what it actually looks like. Here we have, let me grab my pen. We have our offsets, our beginning FF numbers. So this is just us looking at our data file with a hex editor. And then we have our identification. Here we know what they are. They are our JPEG files. And our offsets are basically portions of the data that offset the start of a data file. Here we have our EOI, end of image. We also have a start, I can spell, I promise, start of image, or SOI. And here we don't have the start, we only have the offset, or we only have the EOI, but our JPEG file fits in between the SOI and EOI. So to examine this data, we can use things like autopsy, that's a forensics tool, or any type of exit reader or viewer. All of these tools can extract the metadata, which then we use as evidence to build a case. Here is a directory listing, and we can see, here's the image. We can see what type of file it is. We can see the size. We can see when it was modified or accessed, when it was created. We can see some specific details. However, this isn't a whole lot of detail. Like, this is actually very, very minimal. Where's the image camera type that took the image? Where is the GPS coordinates? So there are other tools that provide a little bit more in depth, and that's again assuming that data was captured with the camera when it was captured. If you take a photo with your cell phone, it is definitely capturing the image, GPS coordinates. It will have the camera data. It will have timestamps, date, location where it's taken. It has a lot of details. So all of our files that we've looked at, all the different standards, JPEG, PNG, TIFFs, all of them compress their data. And that compression might be a GIF or JPEG. Things like a traditional like Windows bitmap, they don't compress their files at all. So you'll notice it's about a little larger. So if we have a JPEG and we have a bitmap of the same file, the bitmap will be bigger. Because again, there is no compression tool for that specific format. There's also data compression, and that's just basically coding the data from a larger to a much smaller form. There are some lossless compressions and lossy compressions. Essentially, when we are able to compress a file, we have to look at how much loss are we going to get, and then we'll look at the ratio of loss versus quality, and if it's a ratio that we're okay with, then we just accept it and we move on. But what does that mean exactly? So lossless compression reduces the file size without removing any data. This is based off a very specific coding algorithm, and it's for redundant bits of data. Utilities are things like WinZip or PKZip or things like that. Lossy compression permanently discards bits of information. So again, lossy is going to remove data bits. While we have our vector quantification, this basically determines what data to discard based on the vectors in the graphics file. That way it can reduce the data, the actual data in the file, but not actually harm the image, or might be a slight reduction. Utilities for this are things like lzip. All of this brings us to what happens when we need to locate, find, or recover those graphic files. Well, the operating system does have some tools, but they are time consuming, and the results aren't always up to par. There are forensics tools that can analyze a disk and pull out specific files. That also works. The image headers are one of those things that we're going to be looking for. For example, a file signature is going to be the hex values for the start of the file or start of the image. There's also the image extension like a .jpeg or .tiff or .png, but those are not as important to the forensics tools. Their extensions are very important to the operating system, but the forensics tools are going to look at the header, the hexadecimal value, and it's going to look for a sequence or file signature to be able to capture that data. The use of the header information basically to create that search analysis or for a baseline. When we're looking at reconstructing image files, we'll have to identify data patterns and modify the headers accordingly. This is typically called carving. Carving or salvaging is basically a mechanism to recover any type of file fragment that is out there. If we're image carving, we are carving out the hexadecimal, specifically looking for an image file. Again, digital forensics tools can carve data from that free space or from the slack space. All of this aids in helping to identify the image file fragments and put them back together to present something that is somewhat readable for the investigator. So a common question is, well, what happens if the header or the file signature is damaged? Well, there are ways to recover. When examining the recovered fragments from a file from either the slack or the free space, you might find that data that appears to be a header. If the header is partially overwritten, partially corrupted, you must have to reconstruct the header to make it readable. And that's a manual process typically. By comparing the hex values of known graphic file formats with the patterns of the file header you had found, you can reconstruct them. And there are some automated tools out there that assist with this. This is just a little bit more pricier for those tools. Each graphic file has a unique header, that is true. For example, the JPEG starts with FFD8. That's the magic number, or that's the start of the file signature, followed by the label as a JFIF for a standard JPEG. Or there could be a EXIF file of an offset for 6. There are exercises that you can use to investigate those data file fragments. That way you can get practice. So in our book, there's an exercise for investigating a possible IP theft by a new employee. Here is the email, at least one part of it. Here's the second part of the email. And then you can actually look and then search for that data. So when we're looking for and carving data from that unallocated space, we can develop a plan for the examination. It's not just willy-nilly, it's structured, it's organized. So when you're searching for a recovering digital file or a digital photograph, for example, we may use a automated tool like Autopsy to search and extract any recoverable evidence files of a specific file type. False hits are referred to as false positives, and you would review them and then discard them if they're not relevant. Here is the process options for configuring the ingest module in Autopsy. Ingest is, again, what you bring in. Here is Autopsy, a little older version, but here's Autopsy. And here we're looking at the parsing EXIF metadata, and you can see the hexadecimal values below. You can see that there are tabs like string and file metadata and results and whatnot. Again, in Autopsy, we can drill down and look at the EXIF metadata so we can see more specific data. We can look at a executable, for example, and we can look at file headers that were overwritten. So here we have a ZZZZ, even though it's a exe. So there are ways to view overwritten values and determine if they are appropriate or not. We can view all sectors used by our data file. Here we're looking at game202.exe, so we can see all of the components, all of the sectors of data that house this data file. Because again, it's not going to be one data file for one storage unit. A data file, depending on its size, might be spread out between multiple sectors of a storage device. So again, if we are searching for data and it is damaged, we are going to have to rebuild them. So before attempting to edit or recover graphic files, try to open the file with an image viewer first. That way you can see if they're functional or not. If the image isn't displaying, you'll have to inspect and correct the header files. And again, the general steps are recover more pieces of the data file if necessary, examine the file header, compare it with a good header, and then test a corrected file. So here's an example of an error message when you're looking at a damaged data file. Here's an example of our offset. So let me grab my pen. So here we have our offset 0. Here we have our offset 6. And we already know that our JPEGs typically have an offset of 6. If we, I'm going to go back one slide. Our offset, because of the header modification, changed it to ZFIF with a 7A, 7A. If we go to the next slide, if we actually do a correct header, so changing the Z back to an uppercase F, we should notice our correct offset. That then possibly will allow us to view it. So what does this mean? When we're looking at these offsets, we can look at our hexadecimal values. So the first hexadecimal number, A, or 41, and then our second hexadecimal number, again, 4, 1, A. If we're looking for the lowercase, 6, oh, nope, 6, 1. These are our hexadecimal numbers for rebuilding our file in ASCII. Once you fix it, you should be able to open the data file. This is called reconstructing from a file fragment. Locate the non-contiguous clusters, or locate the damaged port of the data file that makes up the contents of that file, and correct it. If we're talking about reconstructing from our file fragments only, you're going to have to locate and export all the clusters of the fragment files, determine the starting and end cluster numbers of each fragment group of the sector, copy each of the fragment groups to the sector, and rebuild the file header. Add the appropriate extension, and go from there. Realistically, you're not going to be doing this by hand. You're going to be doing this via automated tools that will be helping you. This you're not going to be doing by hand. That's just not realistic, especially for a entry-level forensics analyst or forensic specialist. When we're dealing with identifying unknown file formats, that's always fun because they may be unknown. So knowing the process of each of the file formats and how it stores data is kind of important for our investigators. You're going to be searching, looking at things like fileformat.info, extension informer, or even graphic file format pages to help identify this content. You're going to be analyzing graphic file headers. So again, most of what you're going to be doing is looking at the header for details. When we're looking at the header, we're going to be using a hex editor, and that will look at the hex values of the data file header so we can examine it. Examples might be looking at like an EXIF file format. While it's a little older, the first 3 bytes of a file should be the same as a TIFF. So that's one of the issues when analyzing just the header is normally the magic number or the first byte is unique, but that's not always the case. So you may need to build your own header search string looking at common file signatures. And realistically, again, this is above what a entry-level forensics analyst individual will need to know. It's more of looking at common file signatures until you build up your experience to be able to go past that. Here we have TIFF file header starting with a 49492A. So this is the beginning part of it. That will identify a TIFF, but it could be a F or an XF instead. So again, TIFF 49492A, equivalent to a II star in ASCII. Here is our XIF, again, II star 49492A in hexadecimal, even though a TIFF and a IF are slightly different. They have the same header, the same general structure. But if we look at more than just the first 3 bytes, then you'll notice there is a difference. So we talked a lot about tools for recovering, looking at the header, but what about tools for viewing? Normally, after you recover any graphics files, you're going to use a viewer to open and view it. No one viewer can read every single format, so do keep that in mind. Photoshop is probably one of the more popular ones and has probably the most robust viewing capability, but it doesn't open up everything. Most graphical interfaces for forensics tools will include an image viewer for common formats. Again, not necessarily all of them, but most of the common formats. Moving past that, what about hiding information inside of an image? That's called stenography. And this is an ancient technique of hiding data. There are 2 major forms of stenography: insertion and substitution. Insertion basically will hide data not displayed when viewing a host file in the associated program. You'll need to analyze the structure to view the contents. For example, here is a HTML file, has a hidden message. When viewing the data, there might be a hidden value. And this is the example of how you would communicate through a web page where it wasn't displayed, but if you viewed the source code, you could see the hidden message. In contrast, we have substitution. This will replace bits of the host file with other bits of data, usually changing the last two least significant bits, and they're going to be detected via stenography tools or stego tools. You should definitely inspect all the files for evidence of stenography, and this used to be more common before encryption or whole disk encryption, but this is still used, just not as frequently because there are different and more clever ways of doing this. Clues to look for when analyzing things like duplicate files with different hash values or stenography programs installed on the perpetrator's computer. So here we might have a original pixel. Here we have 10, 10, 10, 10, and instead the alternating one, we may flip the first and second bit. In this example, we are flipping again the first and second bits. In the third example, again, we've flipped the first and second bit, and so forth. Basically, this is a bit breakdown for a secret message. And when we look at the original file versus the altered file, most people will not see it by the naked eye. However, there is a hidden message in the altered image. This is stenography. The use of stenography tools that detect, decode, and record hidden data are out there. That does mean you have to look for them. Detect variations of graphic files. When done correctly, you cannot detect hidden data. But oftentimes it's not done correctly, so with a thorough investigation and review, you should be able to find most hidden messages. And again, that's not a hard and fast rule. That's not saying all the time you're going to be able to, or all the time you're not going to be able to. There is a difference. So check to see whether the file sizes, image quality, extensions, things like that have been modified. Lastly, we're going to talk about copyright issues with graphics. Stenography has been used to protect copyrighted material by inserting a digital watermark. That's a legal use of stenography. Digital investigators need to be aware of the copyright laws. Copyright laws for internet are not super clear, and half the time general counsel doesn't have a real good understanding, so this makes it a little bit more difficult. There are no international copyright laws, which adds a whole nother layer of complexity. So you do need to check with the local copyright office. If you're in the United States, it'd be the U.S. Copyright Office. If you're out of country, you'd be choosing that country's copyright office. There are other things like fair use, which are other guidelines. Fair use is a type of licensing. All right, so that is it for this chapter. We looked at the types of graphic files, image quality, standards, non-standard file formats, looking at data compression. We looked at what EXIF data is. We looked at the concept of recovering data files and carving. We looked at some software for editing and viewing. We looked at stenography, forms of stenography, insertion, substitution, stego analysis, and then we looked at copyrights. Again, a lot of these components are going to be practiced in our labs, so this is just the lecture component getting core concepts. We will be doing labs to reinforce what we have talked about. Thank you. All right, now that we've wrapped up some of the material for this chapter, are there any questions? There's a lot of different material covered, so again, the key thing is, as you're going through the material, whether it be the reading, whether it be the videos, ask questions, write questions down. The more that you can engage your brain in this material, the better you are at retaining the information. So again, questions, please feel free to reach out and we will go from there. Thank you, and I look forward to working with you throughout the remainder of these modules.